Thank you for joining us on our call today. My name is Nicole Van Wert from Transcat, and I'm going to be your moderator this afternoon. Our webinar topic is In the Field or in the Shop, Overcoming the Challenges in Pressure Calibration. This topic is being presented by Tim Francis from Fluke Calibration. Tim is the Product Marketing Manager for Pressure and Flow at Fluke Calibration. He began his career in pressure metrology in 2002 at Ruska, where he served in a number of different engineering roles, including applications engineer. He joined Fluke Calibration in 2010 following the Ruska acquisition. He holds a bachelor's degree in computer science from the University of Texas at Austin, and he has an MBA from Arizona State University. Tim works in Fluke Calibration in the Phoenix, Arizona facility. We expect today's presentation to last roughly 30 minutes, and then we'll open it up for Q&A. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Tim.
Thank you, Nicole. Welcome, everyone. Thank you for joining us today. As Nicole said, my name is Tim Francis. I'm from Fluke Calibration, and I have the honor and privilege of talking to you today about pressure calibration. A brief agenda of what we're going to be going over. First, we'll cover the vocabulary. Make sure that we're all using the same terms to mean the same things, especially in terms of this presentation, but just overall. There's a lot of vocabulary that's unique to pressure calibration, and in order to make sure that we're increasing our overall knowledge base, we need to make sure that we're using the right vocabulary and the same vocabulary to mean the same things. We'll then talk about some of the different challenges that those doing pressure calibration face, and especially those that affect the decision and the challenges associated with doing calibration work both in the field and in a laboratory type environment. And as Nicole said at the end, we'll leave some time for questions and answers. So let's move first into the vocabulary. And the first subject that we're going to cover is what's called reference modes. You'll often see pressure values followed by certain words like gauge or absolute. You could also see it kind of truncated or shortened to say PSIG or PSIA. And the question is, well, what exactly does this gauge or absolute mean? What is a PSIG and what's a PSIA, and are they different from each other? And how does that affect our calibration process? What do we have to do differently if the pressures in question are gauge versus absolute? The first thing we need to consider is that measurements are relative. Kind of goes back to Einstein, the theory of relativity. Everything is relevant. A relative measurement is definitely one of those as well. And what I mean by that is that you don't say, I live 5 miles. That just doesn't make sense. You have to say, I live 5 miles from here, or I live 5 miles from my work. Everything has a starting point. If you're putting in the directions in your phone, or looking for directions in your phone, it's going to tell you how to get there from where you are. It's not just, it just doesn't make sense to say, well, directions to this place without saying what the starting point is. Well, pressure is the same way. You've got to have a starting point. Saying that the pressure is 5 psi and only saying 5 psi doesn't say the whole story. It doesn't give you all the information that you need. The long way of saying it, the more proper way, would be to say something like, the pressure is 5 psi above atmosphere. But that's kind of a long-winded statement and will not be very effective when you've got a lot of different pressure values that you're looking at. So the terms gauge, absolute, and differential are simply shorthand for this. So we'll look at gauge mode. Here, everything is referenced to atmospheric pressure. So if you have your dial gauge or pressure transmitter, your pressure measuring device, and you have its test port opened up to atmosphere, just opened up to the air in the room. Then it's reading 0, and that means your test pressure is the same as atmosphere. This is probably the most common reference mode, just because it has a lot of usefulness. When looking at this mode, you can see values that are both positive and negative. And simply that's saying is that if it's positive, then that means you have more pressure in your test vessel and in your system than what you have in the atmosphere in the room. If it's negative, that means that you have less pressure, and the number is how much less pressure than what's in the room, what's in the atmosphere. And gauge mode can usually be the easiest to measure. There's a lot of different devices that can measure gauge mode pressures. They can be easily operated and what we call easily zeroed. And so they're abundant and useful. Some examples of different gauge mode measurements are things like the pressure in your tires. So when you're filling air in your tires and you've got your little tire gauge, the pressure that it's displaying, that it's outputting, is a gauge mode measurement. What you're interested in is how much more pressure is in my car tires than in the atmosphere around them. So it has, and it's used quite frequently in many different process measurements. You could also, for example, use it to measure the pressure in a football, like perhaps if you're a New England Patriot. Absolute mode, now you're referenced to a perfect vacuum. And we see that in a diagram to our left, or to the right, excuse me. In this diagram, we show that there's this blue line that's moving all around. That is our barometric pressure, or atmospheric pressure. Gauge is simply the difference between that blue line and our test pressure. So that's represented by this red. And it can be a plus or a minus, plus being above pressure, above atmosphere, minus being below. Absolute pressure is referenced to a perfect vacuum. So that's where one end of the line is down at 0, and so this blue line up at the top is an absolute pressure, and shown in this case to be a stable absolute pressure. So if you have a reading in absolute mode and it says 0, that means it is a perfect vacuum. If it's 0.00000, that's a perfect vacuum. Absolutely no molecules in the system, no pressure whatsoever. That's kind of a theoretical point because it's extremely difficult to get every single molecule out of the system, if not impossible. But what this also tells us is that absolute pressure can only be positive numbers. You can't have negative number of molecules in a vessel. Makes good sense. You can have molecules in the vessel. You can have 0 if you try really hard. Theoretically, you can't have negative. So if somebody were to say that the pressure is -1 psi absolute, that wouldn't make any sense. That would not be a viable pressure measurement. Absolute pressure can be a more difficult measurement, but an extremely useful measurement. And the challenge on what makes it a more difficult measurement is re-zeroing the measurement device, re-zeroing the reference. What we mean by that is that just about every measurement device, pressure measurement type device, will suffer from what we call zero drift. That is that over time, the reading of the device will drift, where it will have an offset throughout its entire range. And this is what we would call zero drift. With a gauge mode device, it's very simple to resolve this. Open the device up to atmosphere, and if it's open to atmosphere, then you know it's seeing 0 gauge pressure. So you simply take whatever the reading is, you subtract that off so that you get a 0 reading. And you do that, you subtract that value off throughout the entire range. Most devices, most calibrators have a function to do exactly that. With absolute mode, it gets much more difficult because the only place where it should specifically read 0 is at a perfect vacuum, which, as we said, is pretty much impossible. So to read 0 an absolute device, you really need a device that's more accurate than it that you 0 it against. So if you turn your device on, you open it up to atmosphere, it's reading something like 14.7 psi absolute. You then have a very accurate barometer that tells you that no, actually the barometric pressure in the room is 14.685. And so you know that, okay, we can correct what, instead of 14.7, it should be reading 14.685. That means that you need that other device. And so a lot of times, instead of zeroing it as a routine process, it gets zeroed as part of the calibration process once a year or so, 6 months, a year, whatever the calibration interval is. And so you've got to include that zero drift in the overall accuracy of the instrument. It's not an impossible situation, but it does make it slightly more difficult than your normal gauge mode calibration. Some examples of absolute mode is the barometric pressure measurement. So as we said, the pressure in the room is, by definition in gauge mode, is 0. So that's not very useful to us. If we want to know what the actual barometric pressure is, and that's useful information to have to figure out air density and other factors. But if we want to know what that barometric pressure is, then we have to look at what is the pressure in the room in comparison to a perfect vacuum. And standard barometric pressure, which is defined at sea level, is approximately 14.7 psi absolute. That barometric pressure will change depending upon weather and other conditions. Other examples of an absolute mode measurement is the altitude of an airplane. As I said, 14.7 psi is the barometric pressure at atmosphere, or excuse me, at sea level. As you go up in altitude, then the barometric pressure gets lower and lower. An airplane's altimeter makes use of that fact to determine what the altitude of the airplane is. It's basically measuring the pressure outside of the aircraft in an absolute format, and can then calculate out what the actual altitude of the aircraft is based upon that pressure reading. Another example, in like the oil and gas industry, are downhole tools. If you're measuring the pressure at the bottom of an oil well, you can't really reference that to atmospheric pressure. You can't open one side of your device up to atmospheric pressure because you're a few thousand feet below the ground. So the pressure measurement from a downhole tool is oftentimes an absolute mode measurement. The third main reference mode is what we call differential mode. And that's where your pressure is referenced to another pressure. In many ways, you can think of all pressures as being differential mode, just gauge and absolute being special types of that, where the other pressure that you're referenced to is either atmosphere, in the case of a gauge mode, or a perfect vacuum in the case of an absolute mode. A differential mode is just saying that it's referenced to another pressure. And one of the key examples of that is a line pressure where it's referenced to a much higher pressure, which is like what we see up here, where you've got these two yellow lines. The bottom line can be thought of as the line pressure, and the differential measurement is just how far different are we from that line pressure. So 0 means that there's no difference in the two pressures, whereas a positive pressure means that your test pressure is slightly higher, or a negative would mean that your test pressure is slightly lower than your line pressure. As I said, gauge mode can be thought of as a special case of differential mode, where the line pressure is atmosphere. And this can be, while we say that gauge mode is pretty easy, differential mode can be much more difficult, especially if you're looking at the case of that high line pressure, where the pressure that you're comparing against is much higher than your differential pressure. And an example of that situation is a flow measurement in a pipeline. The overall line pressure of the pipeline may be a couple of thousand psi. To determine the flow of the fluid through that pipeline, you may put an orifice in place. As the fluid flows through that orifice, it'll create a pressure differential across the orifice where the pressure on one side is higher than the pressure on the other side. And if you know what that pressure difference is, then you would be able to calculate out what the flow of the fluid is. That pressure drop is much lower than the overall line pressure. So if the line pressure is a couple of thousand psi, that pressure drop will most likely be lower than, say, 30 psi. So it can make the overall measurement pretty difficult. Another example of differential mode is what we call a draft range measurement, and that's where you're looking at the difference in pressure between two rooms. A key example of that would be rooms that you've got a positive pressure in, such as the operating room in a hospital. They're specifically designed so that when you open the door, none of the germs from outside of the operating room get sucked into the operating room, but instead the other way happens. That the air from inside the operating room moves out towards the outside. And you do that by having a higher pressure inside of the operating room versus the outside room. So you're interested in seeing what the difference is between those two rooms, and that in essence is a differential pressure measurement. We refer to it as draft range because it's a pressure that can be generated just by the draft of a pressure, draft of air. And that leads us into our next discussion, which is how high is high pressure and how low is low pressure. There isn't an official definition. So when somebody says this is high pressure, that may mean something different for different people. What I've provided here is kind of a general outline, is what I'll use during the course of this presentation. The term vacuum is anything less than atmosphere. You can then get into low vacuum and high vacuum is actually the lowest number of molecules. Draft range is that low differential or gauge mode pressures. So it's the difference in pressure between two rooms. A very, very small amount. Oftentimes it will be measured here in the US in a unit like inches of water, or internationally using Pascal or millibar. Medium pressure, or excuse me, low pressure, are pressures that will normally use a pneumatic device to do the calibrations, oftentimes 300 psi or less. This is basically because that's a pressure that's easy to generate by hand with a pump. You are seeing those pressures, that pressure range kind of increase over time, but traditionally what we call that low pressure or pneumatic pressures is in that 300 psi or so. Medium pressures is a range where you could see both pneumatic or hydraulic being used. An example here, so generally between 300 and 2000 psi. And the break-off there is more because a pneumatic pressure is still readily available in most places up to 2000 psi because you could use like a nitrogen bottle as your gas supply. High pressure is almost always hydraulic unless you're concerned with contamination. You can't use hydraulic. And that's 2000 to about 20,000 psi. And so these are pressures where you use hydraulic because it's easier to generate higher pressures and it's a bit safer. And then very high pressure, looking at things greater than 20,000 psi. Our product line can include measurement devices up to 60,000 or even 75,000 psi. Sometimes there's need for higher, but it's a very rare case. As I said, there are no official rules on this. This is just kind of a general statement to give a frame of reference. For some people who focus in on or specialize in one particular range, they may consider everything else as being high pressure. Like, for example, if all you do every day is work in the draft range, then even 300 psi is really high pressure for you. Now, there are some challenges that are created by these different topics that we're looking at here, specifically reference mode. And we'll look at each of these questions individually. Of, if you only have a gauge standard, how do you calibrate an absolute device? Or you see things like negative 15 to 30 psi, but I can't get down to negative 15. We'll talk about some of the challenges with differential devices and also some of the unique terms like sealed gauge. What does that mean? And how is that different from gauge mode? Let's look first at a situation where you're needing to calibrate something that's an absolute mode device, but all you have is a gauge standard. First thing you need to consider is that there will be an offset that's equal to barometric pressure. So if you have an absolute device under test and a gauge mode standard sitting next to each other, one of them, and everything's opened up to atmosphere, one of them will be reading about 14.7 psi and the other one will be reading 0. And that offset, the amount of that offset, will change with barometric pressure. So when you first turn them on, they may be reading 0 and 14.7 psi. As you sit there, the barometric pressure in your room changes. One of them will continue reading 0, and the other will read, say, 14.3 psi. So you've got an error that's just a more or less continuous offset, but the amount of that offset will change with barometric conditions. If you're working with high pressures, so if you're at 10,000, 20,000 psi or higher, these problems may not be an issue for you. You can just estimate what the barometric pressure is, add it to your standard reading. So if your device under test is reading 14.7 at atmosphere, and your standard is reading 0, you just add 14.7 to your standard as an estimate of barometric pressure, and make the assumption that it's not going to change enough that at 10,000 psi or 20,000 psi, that the amount that it changes will matter. Because there, you may only be looking at what's the pressure plus or minus a psi, or plus or minus 2 psi, plus or minus 10 psi. If that's the case, then if your barometric pressure changes by 0.1 psi, it doesn't really affect your overall measurement. With lower pressures, that's not necessarily valid. In those situations, you'll need to measure barometric pressure and continually adjust your standard reading to compensate. So if you have a barometer, then at atmosphere, while your standard is reading 0, your barometer is reading 14.68. So you know, okay, my actual pressure is 14.68. As you go up in pressure, your standard may be reading 1,000, and your barometer is reading 14.7. So now you know that the actual pressure is 1,014.7. That will allow you to continuously adjust and take into account the changes in barometric pressure when you're trying to calibrate an absolute mode device using a gauge standard. A common question we get is, okay, your data sheet says negative 15, but I can't actually get to negative 15. The thing's broke. What's wrong with it? Well, let's step back and look at it a bit. At barometric pressure, we've defined that barometric pressure is 0 psi gauge. It's also approximately 14.7 psi absolute. So we're now saying that I want 15 psi below barometric pressure. That's negative 15 psi gauge, which is negative 0.3 psi absolute. That's not physically possible. As we said, absolute pressures cannot be negative. Absolute pressure is always positive. So it's just not physically possible. It doesn't matter how good of a vacuum pump you have, how leak tight your system is. You can't go any lower than -1 times your barometric pressure. And that's going to be different at different locations throughout the world. And the biggest determiner is altitude. So like Denver, Colorado, it's at a mile high, you're approximately 12.1 psi absolute. So the lowest you could possibly go in a perfectly leak-tight system with the most powerful vacuum pump is negative 12.1. Honolulu, Hawaii, right there at the beach, you're at sea level, you can get to negative 14.7. But if you climb to the top of that volcano, where you're much higher, in fact, you're more than a mile up, now your atmospheric pressure is only 8.7 psi absolute. So the lowest you can possibly go is negative 8.7. So why do we say negative 15? Generally speaking, that would be it's rare for atmospheric pressure to be greater than 15 psi. And in reality, it's more just a rounding situation. You have to be cognizant of your location, your barometric pressure, and seeing what it is. So even at sea level, it may not be possible to get negative 14.7, but at the same time, that's your best case is at sea level. So if the auditor or your manager is complaining saying that, hey, this device has a range from negative 14 to 0 or negative 14 to 30, but you only went down to negative 12, tell them, well, we need to do this calibration at the beach. Let me go to the beach, and then we can get it down to negative 14 for you. A very big challenge is calibrating something at a high line differential. Once again, what we mean by that is where the line pressure, the starting point, is a very high pressure. And then we're measuring the test pressure as being slightly different from that line pressure. So the example here is a pressure transmitter used on a pipeline, and so that pipeline has a pressure of about 1500 psi absolute. And it's measuring the drop in pressure across an orifice. And that drop in pressure is about 30 psi. That would be 30 psi differential. Generally speaking, it's always best to calibrate a device as similar to how it's used in the real world as possible. So that way your calibration adequately covers the potential errors that the device is used in its normal application. If we're going to do that in this case, then we need to apply 1500 psi to one side, 1500 psi absolute to one side of the transmitter, and 1530 psi absolute to the other side. That's difficult to do and to measure correctly. We could do it by, we could have two absolute mode standards and of say 2000 psi absolute full scale, and we apply those pressures and read them off of there, but our overall error in terms of the differential will be quite high. So that's difficult to do. So it's commonplace to normally leave one side open to atmosphere and apply 30 psi to the other side. So there, you're still measuring the same differential. You've got one side of so a differential style device will always have two test ports, a high and a low. The pressure on the high side is 30 psi greater than the low side. The difference being that when it's actually used, it's still 30 psi different, but the low side is 1500 and the high side is 1530. Here, it's 30 psi, it's 0 on one side, or atmosphere on one side, and 30 psi higher on the other. Is it okay to do that? It depends on who you ask, but in most applications it is acceptable. There's also a term called sealed gauge. And what does that mean? It's kind of a hybrid of gauge mode and absolute mode. In this case, if the test port is open to atmosphere, it reads 0, just like a gauge mode device. But if the barometric pressure changes, then the measurement will change with it, like an absolute mode device. So basically it's reading gauge, but it's or a gauge-like reading, but the backside of the measuring device, of the sensor, is sealed off and is not actually open to atmosphere. So it doesn't stay at 0 with atmosphere changes. So it's similar to using an absolute mode device and subtracting a default barometric pressure value from it. And this is useful for high pressure applications where the variations in barometric pressure don't affect your overall measurement. Okay, so we talked about the agenda and we looked at some of the challenges associated with the agenda, or with the vocabulary. Let's look at some more challenges that affect calibrations. First thing, as always, is we need to consider safety. A pressurized vessel has some inherent safety risks. So make sure that all equipment is rated to the proper pressures for the work being performed. There's different ways to do this. Some shops will only stock pressure lines and fittings that are rated to the highest pressure they possibly work at. That works well if the highest pressure is relatively low or they're only working in one region of pressure. It doesn't necessarily work if you do both draft range and 20,000 psi, because the lines that will work for 20,000 psi don't work very well for 1 inch of water. You need to make sure you use the proper PPE or personal protection equipment, such as safety glasses. And when working in the field, be cognizant of the dangers around you. And the safety of the calibration technician should be a key concern when determining if you should do a calibration in the field or back at a laboratory. If the device is installed in a location where it's not safe to do the calibration, then it should be taken back to the laboratory or the shop to do that calibration. You also need to make sure that you have the equipment that is right for that area. If it's in a intrinsically unsafe or a hazardous environment, potentially explosive environment, then you need to make sure that you have intrinsically safe devices. We also need to look at the impacts from the environment on our calibration. For example, temperature. Almost everything that measures pressure is also impacted by temperature. So a pressure calibrator manufacturer, such as Fluke, will characterize and compensate our pressure measurement devices, our calibrators, so that they can work at different temperatures. But they'll still perform best over a given temperature range. Depending upon the device, that may be 0 to 50 degrees Celsius, or perhaps even wider, or it may be as limited as, say, 18 to 28 degrees Celsius. Some pressure measurement devices, specifically deadweight testers, are impacted by gravity. The acceleration of gravity will alter the pressure value that the deadweight tester is generating. And that can be by a very large amount without going into too much detail. So when you're, so one of the ways that the environment impacts our calibration is the local gravity. The acceleration of gravity is different at different locations. And we need to take that into consideration at the location where we're doing the calibration. If our deadweight tester has been built for a specific location for our shop, and we're moving it 100 miles or so down the road, then the local gravity may change, may be different, and we need to take that into account. Another thing to consider is what we call head height. That is the difference in vertical elevation between the reference and the device under test. And what it will do is create an error. Basically, the weight of the fluid will generate its own pressure. And you can think about that as if you're in a swimming pool, the pressure at the top of the pool is much less than the pressure at the bottom of the pool. Same thing applies here, and the phenomena occurs whether it's gas or oil. Even a column of gas can create a pressure. Even though we don't think of it as weighing anything, it really does. So 3 feet of gas, that could be less than a 0.01% of reading, but 3 feet of oil is about 10 psi. What this means is that at lower pressures, gas is a preferable medium, whereas because at low pressures, 10 psi might make a very big difference. But when you're measuring 10,000 psi, 10 psi might not matter nearly as much. Large drafts, temperature swings, or changes in barometric pressure can make it difficult to get pressure to stabilize. And that's a huge thing that we need to consider when we're looking at the environment that we're doing our calibration in. Another thing to consider is contamination. Dirt, debris, and liquids from the device under test can cause problems. They can damage your calibration equipment, it can cross-contaminate other devices under test, and just play havoc in your overall system. How do we combat it? Clean the devices before we connect to them, make use of filters, traps, or separators, have separate pressure lines and fittings for different types of fluids so that you have one set that's used with oil and another set that's just used with air, so that way you don't get oil into your air systems. Examples of filters or traps or separators can be used. Shown here is at the top is an example of a separator. Here you've got, on the bottom is where you can connect to your reference, at the top is where you can connect your device under test, and there's a diaphragm in the middle. So when you change the pressure below, it pushes up on the diaphragm and changes the pressure above, but the media never actually comes in contact with each other. This works great on an higher pressure oil system. A separator or a trap is like this device below that has the clear acrylic walls. Your one side, say your device under test is connected to the top, and your reference is connected below. For the pressure to go, or the debris to go from the device under test to the main unit, it's got to go up or go down, back up, and back down again, and that acts as a gravity trap that will keep the debris from reaching the standard. So finally, that brings us to the question: how do we decide if we do our work in the field or in the lab? We need to consider a few questions. Can it be done safely in the field? And does the environment allow for the calibration to be done properly? Obviously, or one would hope that the device that we're testing, that the environment that it's installed in is appropriate for that device. But we also have to look at what environment is appropriate for our reference standard. It may only work under a much smaller temperature range, or it needs, we need to know local gravity for it. So is the environment appropriate for our calibration overall? Or are there wind drafts or other things that cause it to not be able to get a stable enough pressure to get a good reading from our reference? And can you easily connect to the device under test? Is it a situation where you're going to have to run 1,000 feet of hose up to our device under test in order to apply pressure to it? Well, that's 1,000 feet of head height offset. Or is it a situation where it's better to calibrate a similar device? So if it's a pressure transmitter, we've got two of them that are very similar to each other, or that's the same model and range and everything. Calibrate one in the shop, rotate it into the field, bring the other one back for calibration. These things need to be considered when making that choice. And then finally, we need to make sure we have the right equipment. So make sure you have devices that cover the proper range and mode. If you've got a device that's only a gauge mode device, reference, but you routinely need to do absolute mode calibrations, then look at, are there pressure modules or other such things, or maybe you need to get another device that can do absolute mode, so you can make sure that you're not inducing additional error that doesn't need to be there. It's also not always appropriate to calibrate low pressure with a higher range instrument. The errors and inaccuracies of the measuring device are oftentimes a function of its range. So if the device, if you've got a gauge that's 1,000 psi and you're trying to measure 1 psi with it, it may not work very well for you. But some examples, but once again, that's something that could possibly you can get around by adding pressure modules or similar with it. An example here is like the Fluke 3130 that we show here with a 750p pressure module. The 3130 has an internal range of 300 psi gauge. If I wanted to calibrate absolute mode devices, I can simply connect an absolute mode 750p module, or if I want to calibrate very low ranges like a draft range or high pressures, I could possibly do the same by adding those range 750p modules as well. Other things to consider is portable versus bench. Portable type instruments, like the Fluke 718, they can be used on the bench and work well there, but depending upon them, that's not really necessarily what they're designed for. So they're designed for the field, and they will work much better in the field, so they aren't always ergonomic for the bench. But depending upon your use case and your situation, it could work just fine for you. So in conclusion, pressure calibrations can be challenging, but these challenges can be overcome with the right processes and the right equipment. Okay. And so I will turn it over to Nicole now to go over any questions.
Okay, before we go into the questions, I just wanted to make everyone aware of a special limited time offer that's going on right now. With Fluke and Fluke Calibration, there's a gift with purchase offer where for purchases over $250, there's tiered gifts with purchase. There are 7 tiers starting at $250, and I think the top level might be over $10,000 purchases, but you can choose a gift with purchase valued at up to $1,200. So if you'd like details on that, you could go to transcat.com/deals, or you could always contact me directly at nvanword@transcat.com. Or call anyone on our sales team. Everyone's aware of the promotion, so it's a good time to buy. Okay, so let me remind you that any questions, if you have any questions, you can submit them through the question box in your webinar controls. It's on the right side. We've got a couple questions already, so I'm going to go through them. Okay, let's start with this one. What is the difference between gauge and bidirectional gauge?
Okay. You'll also see the term bidirectional gauge, and that simply means that it can read both negative, so subatmospheric pressures, as well as gauge pressures, or as well as positive pressures. So gauge mode oftentimes can mean just 0 and above, is how some companies will consider it, whereas bidirectional means that it would read from, say, -5 to +5 psi, or -15, or -14.7, up to 15 psi.
Okay. Can relative humidity affect pressure calibration?
Okay, so the question is, can relative humidity affect pressure calibration? Well, at some level, just about anything can affect pressure calibration. So the short answer is yes. How it can depends upon the instrumentation that you're using. There are some measurement devices, first off, some pressure sensors that are susceptible to humidity, where if it's more moist, then they may give a different reading. The other thing is that humidity, a very dry climate, for example, could possibly affect the electronics that are being used inside the instrument. Or another example is that a deadweight tester is impacted by the density of the air, which is impacted somewhat by the humidity. Just about every instrument will have a humidity specification of saying that, okay, the humidity must be within this range and normally non-condensing for the instrument to work correctly. So you should pay attention to those situations.
Okay, next question. When a device under test spec doesn't define the inches of water temperature, what is the industry standard temp?
Okay, so the question, and I'll expand it a bit. So the question on inches of water, if it doesn't define the reference temperature, then what is it? What's the industry standard? So first off, there's a measurement unit called inches of water, and it's based off of pretty much the same phenomena as head height, in that pressure can be defined as the density of the fluid times the height times gravity. So, and the pressure unit inches of water is the pressure that's associated with a column of water that's 1 inch high times standard gravity and times the density of water. Well, the density of water is not constant. It is different depending upon the temperature of the water. So while you have this measurement unit called inches of water, you have, in reality, you've got about 3 or 4 different versions of it where it's inches of water at different reference temperatures. The most common ones would be like 4 degrees Celsius, as that's where the temperature of water is most well known, and that's where it's the highest density. Or also 20 degrees Celsius, as that's a very common reference temperature. especially for dimensional measurements. So the question is that if the device just says inches of water and doesn't say what the reference temperature is, then which one do you choose? And is there an industry standard? To the best of my knowledge, there is not an industry standard across the multiple different vertical industries and so forth. You'll see perhaps in like the natural gas industry, I think is more of a 23 degrees C, but I'm not 100% positive on that. And other industries will pick others. I would say always contact the manufacturer of the device and find out. If they don't know, it may mean that the difference in the densities is such that it's not going to impact the overall, that the accuracy of the device is, for lack of a better word, so bad that it's not going to, that the differences in density won't matter. But some people are also just not aware of the situation. Excuse me. I would suggest that your laboratory set up a policy where you always use the inches of water that's defined by the manufacturer. So especially if it says what it is, then you make sure you match that on your reference. If it's not defined, then you pick one as your definition. Personally, I'm a big fan of 4 degrees C. And that on your calibration reports where you're using inches of water, that you define what the measurement conversion factor is that you used. So each of these, while their history and their definition is based off of a column of water, it's not very frequently that they're actually used. They're actually measured with a column of water anymore. They're using some sort of electronic sensor and so forth, and it's just converting from, say, Pascal to this inches of water. So if you include what the conversion factor is, then everybody knows, okay, here's how to get back to a real measurement unit.
Okay. I think we've got about 5 more. If gauges are going to be used at ambient temperature, should they be calibrated at that temperature or under temperature control?
Okay, so the question is, if they're going to be used at ambient temperature, what temperature should they be calibrated under? So the more general question is, do you need to calibrate a device at the same temperature where it's going to be used? Generally speaking, you can calibrate the device at ambient temperature and be okay, and not necessarily at a control temperature. When we manufacture a new device, we will characterize it at multiple temperatures. So we'll put it in an oven, run our environmental chamber, run it at low temperatures, at high temperatures, look at the pressure output at those different temperatures, install a bunch of coefficients into the device, and correct for that. The calibration is then put on top of that as the final characterization, or the final calibration of the device. For most devices, the behavior with temperature doesn't change with time. So the overall behavior of the device will change, it will drift, so you can recalibrate it at one temperature and know that it will work at all the temperatures within its range. There are situations, depending upon the design of the device, where the calibration instructions will specifically say that it needs to be calibrated at a given temperature plus or minus X number of degrees. And I do that because that final calibration run is assuming that it's being used, or requires it to be used at that particular temperature, so that so you don't end up having the temperature effects in that final calibration run, but those stay as part of the compensation process. So generally speaking, pressure calibrations are oftentimes, when you recalibrate a device, it's just done at ambient temperature. Always check the user manual of the device you're calibrating and make sure that that's okay. It's rare that as part of the recalibration process that you'll need to put it in an environmental chamber or something like that to keep it at a constant temperature.
Okay. When calibrating to 87,250 psi, is a deadweight tester applicable?
So it's 87,250 psi. There are deadweight testers that will go up to that high of pressure. I can't speak to them and their usability, as we don't actually. The highest that we manufacture up to is approximately 75,000 psi. But you will see a particular design of deadweight tester that can go to that high of pressure.
Okay.
Not very common though.
Okay. You mentioned gravity as a consideration when calibrating. With a distance of only 100 miles, that was your example, how different is the gravity between two places? The wide open one.
Yeah, so how different is gravity between two places? It really depends, because like if it's a function of like altitude, the distance from the equator, and geological conditions. So it's possible that you can find two locations very far apart that have very similar gravities. But at the same time, like if you're going from the south to the north and you're going up a mountain, or there's a geological formation difference, then you could see a very large difference in the acceleration of gravity. There are a couple of websites available. One that's specifically for the United States by the National Geological Society, I believe, and then also one done by PTB in Germany for the entire world, where you can put in the latitude, longitude, and altitude of a location or elevation of a location, and it will provide you with the estimate of the local gravity of that location. So in your particular case, you can put in the two different locations that you're interested in, be it your shop versus 100 miles down the road, and see how different those two are. To find those tools, obviously you can search the internet, but if you go to flukecal.com, we have an application note that talks about this and provides links to those two tools.
Okay. What method would you recommend for sourcing low differential pressure, for example, 0.25 inches of water column?
Okay, so so low differential pressure, 0.25 inches of water column. To give everybody reference, that's a quarter inch of water. That's definitely a draft range pressure measurement, one where the wind in the room, if somebody sneezes, you could possibly see it in your pressure measurement. And the question is, well, how do you source that sort of pressure? There's different tools that are out there to do that. You can use a small variable volume. There's also pressure controllers that are capable of doing that. An example is one from a company called Cetra. As a portable device that's capable of providing a stable pressure. We manufacture laboratory devices that can provide very stable pressures at that sort of pressure range. There's a whole set of challenges associated with having a stable low draft range pressure like that, because as I said, if somebody sneezes, that will cause your pressure to move around. So you need to make sure that your reference is isolated from atmosphere, so that when somebody opens the door, it doesn't change your pressure. And look at ways to perhaps increase the volume on the reference side and on the test side, but also make sure those volumes are more or less the same, so as the temperature changes, it affects both sides equally. Those sort of tools, you can use a manual device, as I said, a variable volume, where it's just changing the volume in the system a slight bit, or there's also automated pressure controllers available that can make it easy to do that.
Okay, last question. What should the accuracy of the reference instrument be in comparison to the test instrument?
Okay, so that is a very wide open question as well. So it's what should the accuracy of the test instrument or the reference be in comparison to the test instrument. So normal calibration, you've got a device that you're testing, and you've got some device that's more accurate than it that is your reference. And the question is, well, how much more accurate does it need to be? There's not a proper answer I can give in 30 seconds or less. There are some rule of thumbs that have been used historically. At one time, a rule of thumb was something like 10 to 1, but it's much more common now to see 4 to 1. So if your device-centered test is plus or minus 0.1, then your reference would need to be something like 0.025. So it's 4 to 1. The long answer, the more correct answer, is you'll need to do an analysis of the uncertainty associated with the two devices and consider that in your overall determination. There are situations, and 4 to 1 happens to be a situation where statistically the uncertainty, the accuracy of your standard has minimal impact on the accuracy of your device-centered test. There are situations where lower than 4 to 1, 3 to 1, 2.5 to 1 is actually acceptable and very common. And so it shouldn't just be immediately discounted as not being acceptable, but should be evaluated for the actual application. If you have a mission-critical measurement, one that if the device is out, it's going to result in a large amount of recall or potential safety hazard, then you may want to err on the side of caution and have a higher test ratio.
Okay. All right, it's just about 3 o'clock, so that concludes our time for today. If you have any further questions that you didn't submit or would like to find out more about Transcat's product and service offerings, please contact us at 1-800-828-1470 on the web at transcat.com, or you can email me directly, Nicole. My name is Nicole Van Wert. My email is nvanwert@transcat.com. And thanks again, everyone, for joining us today. We hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. And thank you, Tim. Take care.
Thanks, everyone.